All right, so this is going to be a video of the Unit 6 review to give you your answers and kind of walk you through this whole chapter. This chapter was kind of long and we covered a lot of information. Remember, flashcards are going to be your best friend. So here's number 1. Recall your representations of the atoms in the sticky tape lab activity. Below is a pair of tapes before they've been pulled apart. Explain why they would not exert a force, either attractive or repulsive, on one another. Well, this goes to J.J. Tompkins' model of an atom. Remember that he said that he thought atoms were solid objects that had a positive background. So the whole background here he figures is positive. So each of these atoms has a positive background. And then he thought that there were negative electrons that were kind of pushed into the atom. So an atom, as it sits on the periodic table, is going to have a neutral charge. So the amount of positive charge is equal to the amount of negative charge. So they're neutral. If they're neutral, they don't have a positive or negative charge. And this one's neutral too. The amount of positive charge equals the amount of negative charge. So there's no attractive force. Below are the groups of inner core atoms of the tapes after they've been pulled apart. Sketch the mobile negative electrons to show how the top tape becomes positive and the bottom tape becomes negative. Remember when we put those tapes together, they originally started with 3 electrons in each of them, as we've drawn up above. When we put them together, the electrons are mobile. They can actually move. So they moved from the top tape. Originally we had 3. This electron moved down here. So now we've got 4 electrons here. This one here had 3 originally. It moved down to the bottom tape. Now we've got 4. This one here had 3 originally. One moved down to the bottom tape, so now we have 4 down here. And the same thing with this one. This electron moved down, so now we've got 4 electrons. Remember, they started off with a neutral charge. This had a plus, each atom had a +3 charge and a +3 negative charge, or a negative charge. And so it was neutral, but now when we've moved these, we actually have more positive charge than we do negative, making our tapes positive and negative. Now, what evidence allows us to conclude that the top tape was positive? Well, I talked about this in class. It was attracted to a negative charge. Actually, let's say a negatively charged object. And that's where I took the magnets and I put them next to the tape. Unfortunately, as the day went on, the dust in the air started to adhering to the tape, and so as I went through the day, the charged tapes had less and less charge because they were becoming neutral. So below is a group of inner core of a piece of metal foil. Sketch where you would expect to find the mobile negative charges if a top tape, positive, was brought to the left of the foil. Explain your diagram. So remember, the electrons all started off being, let's just draw our 3 electrons. I'm drawing them kind of all in the middle. This is before you bring the tape to it. So this is how the metal looks before you have something positive next to it. When I bring something positive, the electrons can actually move. And they can move right off of their atom and actually move into the electrons to get closer to that negatively charged, or sorry, that positive charge. So my mobile electrons can actually leave the atom electrons in a metal So in nonmetal, they're not going to be able to do this. They're not going to be able to move away from their atom. They're going to be held more tightly. But in a metal, these electrons can actually move right away from their atoms to get closer. All right, the next one says, describe how J.J. Thomson concluded that the mobily charged particle in an atom had a negative charge. Well, remember, in his experiment, he had two plates. And then he had a beam of electrons. A beam of gas particles that was traveling here. This one had a positive charge, and that plate had a negative charge. Well, as the atoms passed through, they were bent toward the positive charge. So if something is moving toward a positive charge, it must have a negative charge. And that's how he concluded that whatever particle, the mobily charged particle, has a negative charge. A solution of salt conducts electricity. A solution of sugar does not. Well, remember, these are two different compounds. Salt is an ionic compound because it's made of a metal and a nonmetal. In this, the electrons are transferred from one atom to the other one, which means the electrons can move, and if you have something where electrons are moving, so electricity is going to go through it. In sugar, it's covalent. It's going to be made of a nonmetal and a nonmetal. And remembering the electrons are shared. When the atoms are sharing electrons, they're going to hold on tightly to those electrons. The electrons are not mobile, and so the electricity can't move through this solution. Below left is a 2D array that represents an ionic lattice. At right is a 2D array that represents a molecular solid. In what ways are they similar? In which ways are they different? So this is the ionic one, and this is covalent, otherwise known as molecular. So in this one we have alternating positive and negative charges. In this one we have no charges. So no charged particles. So that's the way that they're different. How they're similar is that these do have an orderly arrangement. These also have an orderly arrangement. What evidence helps us to conclude that chloride ions have a negative charge? Well, if you put them a positive ion, they will form a bond. How do you decide how many ions of each type combine to form an ionic compound? You balance number of cations with the number of anions to create a neutral charge. So let's say that we're doing a compound that's calcium combined with phosphorus. The first thing I'm going to do is I'm going to look to see what is the charge on calcium. Calcium has a +2 charge. Phosphorus, when I look on the periodic table, or I can look on my cheat sheet, phosphorus has a -3 charge. It needs to gain 3 electrons. So in order to get these to balance out, right now I'm not equal, so I'm going to add another calcium. Now I have a total amount of positive charge of +4. I'm going to add another phosphorus. I have a total amount of charge of -6. If I add one more calcium, now my total charges are +6 on this side, -6 on this side, and it's balanced. So my formula is going to be Ca, I needed 3 of them, P, 2, because I needed 2 of the phosphide ions. Why do ionic solids have higher melting and boiling points than do most molecular solids? Because the ionic bond is stronger than covalent. Why do we use the term formula unit rather than molecule when we refer to the simplest repeating unit of an ionic solid? And that's because they form crystals with alternating positive and negative charges. The formula unit is the lowest ratio of the elements in the compound. Remember, we determined that in the empirical formula. How many ions are formed when sodium or Na2 and SO4 dissolved? In what ways are the positive and negative ions different? Well, the first thing, I'm going to divide this in 2. So I've got my cation side and I've got my anion side. Well, SO4, when I look on my cheat sheet, SO4 is one of the polyatomic ions. So I'm going to treat this as SO4, and that has a -2 charge. When I look on the cation side, I've got 2 sodium atoms. Each sodium atom has a +1 charge. I mean, this is what we did when we were balancing them out. So how many ions are formed when solid NaSO4 dissolves? Well, I'm going to have 3 ions. Here's one, here's another one, and here's the third one. In what way are the positive and negative ions different? These are monatomic ions, and this is a polyatomic ion. Apart from making life difficult for beginning chemistry students, why do chemists refer to CO2 as carbon dioxide, yet use the name tin 4 oxide to describe SnO2? There are 2 different compounds. CO2 is covalent or molecular. SnO2 is ionic. we have to use the Roman numeral to state the charge on tin because it is a transition metal. Of course, I think we've done this next question a lot. Make sure you know which combination of elements give rise to ionic and which form molecular compounds. So ionic is metals and nonmetals. Covalent or molecular
You get one of these?
are nonmetals
Oh.
and nonmetals.